So they have the same spread. The residuals are normally distributed. So LM was a good choice here. This ANOVA table has shown us that the one-way ANOVA gives us one p-value. It says there is something going on in your data. But you still don't know which group is different from which. Is it the cars with 3 gears compared to the cars with 5 gears, or the cars with 4 gears compared to the cars with 5 gears? You don't know. Yeah? So ANOVA is never enough to answer your question. You always have to do additional tests, pairwise comparisons after ANOVA. And these pairwise comparisons, where you're going to pairwise compare the different groups, are called post-hoc tests. And which of tests you use as a post-hoc test depends on what you want to compare. If you want to compare every group to every other group, then you want to use what is called a Tukey's test. How can you do a Tukey's test? Well, you use this function. This allows you to do pairwise comparisons after an ANOVA. And here you define which pairwise comparisons you do. So I will show it in the code. It will become more clear. But you have to tell him explicitly that you want to do a Tukey test. And then he will compare all the groups to all the other groups. Sometimes you want to compare every group to one control. Yeah? Then you don't do Tukey, you do a Dunnett test. The code is exactly the same, but instead of saying I want to do Tukey, you say I want to do Dunnett. And then he will compare every group to one control. You can also specify specific comparisons. So if you don't want to do this and you don't want to do this, but you want to specify specific comparisons that you want to make, then you have to define what is called a contrast matrix. And I'm going to explain that here on the slide because it's easier. So in the contrast matrix, every column represents a group. So if I have 4 groups, then the contrast matrix will consist of 4 columns. The data in the contrast matrix are 1, -1, and zeros. So 0 means ignore. Yeah? Don't look at this. 1 means compare, and -1 means compare to. So in this first line here, I'm defining that I want to compare group 1 to group 2. In the second line here, I define that I want to compare group 2 to group 1. So in this contrast matrix, every row represents a comparison that you want to make, and every column represents a group that you can compare. And the ones and the -1s will define which comparisons you want to make. So these are the 3 ways to define the comparisons that you want to do after a one-way ANOVA. Okay, important. Yeah, why not always use this? Well, Tukey's and Dunnett's tests are tests that look like a t-test. They are similar to a t-test, but they are not exactly the same as a t-test. Yeah? For instance, Tukey and Dunnett will automatically do a multiple testing correction, which should be done here. Yeah? If you do more than one comparison, you're doing multiple tests on the same data set, so you have to do a multiple testing correction. So they do this automatically. And they also take a different approach in estimating the variability in the data than the regular t-test. Yeah? So Tukey, for instance, takes all the groups together to calculate a pooled variance because you want to compare everything to everything. So this makes sense to do. Yeah? And the regular t-test will only calculate the variance based on the 2 groups that you want to compare, yeah? Not all the groups. So Tukey is doing a better job here. When you want to compare everything to everything, then Tukey will be more correct than doing pairwise t-tests and doing a multiple testing correction afterwards. Because Tukey will do a better estimation of the variance than the pairwise t-tests. And the same is true for Dunnett. So if this is what you want to do, use Tukey. And if this is what you want to do, use Dunnett. Only when they do not satisfy your needs, then you go for the contrast matrix. You have no other choice. Well, you need a package called multiple comparisons, multcomp for that. I'm going to load it. And it has this function here, GLHT, which stands for General Linear Hypothesis. Yeah. And it performs multiple comparisons for parametric models. Important, this word parametric. So you use this after an ANOVA. You cannot use this after Kruskal-Wallis because it assumes that your residuals are normally distributed. Okay. So you use this function. What does it need as an input? It needs to have the model, as you can see here, a model. What is the model? The model is the output of LM. That's what LM generates, this. That's the model. And then you have to set this argument, and this argument specifies which comparisons you want to make. Yeah? Specification of the comparisons you want to do. What is the value for this argument? Well, the multiple comparisons function. And here in the multiple comparisons function, you have to tell him what you want to do. So you want to do Tukey's test. Yeah. Which groups? Well, the groups that are defined in the gear column. These groups. You want to compare every group to every other group using the Tukey test. So you do this, you save the results in a variable when I run this, and then you can do the summary function on that result to show the outcome. Yeah? So you see everything was compared to everything, and you see that you have a low p-value below 0.05 for the comparison of cars with 3 and cars with 4 gears. So there's a difference between these two groups. And for the others, you don't have enough data to say that there is a difference. So these p-values are higher than 0.05. And the p-values that you see here have been automatically corrected for doing multiple tests. If you want to compare every group to a control, you use exactly the same code. What is different? Here it is. You say, I want to do a Dunnett comparison. Let's do it. Let's look at the output. Here we are. So less comparisons, because now you're comparing everything to the control. What is the control? The control is by default the group that comes first in the alphabet. So in our case, it's the 3 gears. Again, you see that the p-values are different than here, and they should be. You do less comparisons, and you use a different method. Also here, the p-values have automatically been corrected for doing multiple tests. And how does the contrast matrix work now? Well, I'm going to create one, and then I will show. Here we are. So what do you need to make? Well, you need to make a matrix. The number of columns in the matrix is the same as the number of groups that you have. We have 3 groups, 3 gears, 4 gears, 5 gears, so we have 3 columns in the contrast matrix. The number of rows in the contrast matrix is the number of comparisons you want to do. So each comparison is one row. And then you just have to fill up the matrix with zeros, ones, and minus ones, depending on what you want to compare. So this will compare 3 gears to 4 gears, and this will compare 5 gears to 4 gears. So I have the matrix. These are just names that I give for my convenience, so that I can see in the results which result corresponds to which comparison. So these are just names that I give to these rows. So I row bind these two rows to each other. I provide a name for each row, and I provide the actual values. And then I can do the same code again, but this time instead of typing Q key or donut, I give him the contrast matrix. So I say, compare the groups that are defined in the gear column according to the comparisons that I have defined here in this contrast matrix. So when I do this and I save the results, this time when I ask for the summary, so this here when you work with the contrast matrix, then the multiple testing correction is not automatically done. You have to do it. And when do you do it? You can do it here now in the summary function. You can tell him use a Bonferroni correction on the p-values that you find here. That's what you do here. So when I run this line of code, I get p-values. Corrected p-values because I have added this argument to the summary function.